Welcome back to the deep dive. Today, we're embarking on a pretty critical mission, actually, building your ultimate inspector's roadmap. We're diving deep into some really essential concepts, especially for those of you gearing up for the CSWIP 3.1 Welding Inspector Exam.
That's right.
Think of this as your shortcut, maybe, to sharpening your understanding of key welding principles. We'll be using exam-style, multiple-choice questions.
Yeah, and that format's really helpful.
We'll kick things off mastering the subtle art of process control, then look into the unique challenges different materials present, and wrap up with the critical components that underpin everything.
Exactly. And, while getting the right answer on the exam is obviously crucial, non-negotiable, really.
Right.
Our goal here is more to dig into why an answer is correct. And, just as importantly, why the other options miss the mark.
Okay.
For a welding inspector, that deeper understanding, that nuance, it isn't just helpful, it's absolutely essential for critical thinking on the job.
Makes sense.
We want you thinking beyond just memorizing facts, getting a real grasp of the practical side.
Okay, perfect. So let's jump straight into our first question then and start this journey. Get ready to test your knowledge. Question 1. Spatter may be finely controlled during MIG-MAG GMAW welding by A, adjusting the inductance control.
Yeah.
B, using CO2 gas stock C, increasing the arc voltage D, welding with no gas.
All right, take a moment. Think about that. When we say fine control of spatter, what's the most precise lever you can pull?
Yeah, the correct answer here is A, adjusting the inductance control. And this is honestly a really key point for anyone using MIG-MAG.
Okay.
Inductance control, it directly, significantly influences the short-circuiting arc, how it behaves.
How so?
Well, basically, it controls the current ramps up and down during each short circuit. This affects something called the pinch effect. Think of it maybe like controlling how a drop of water pinches off a tap.
Ah, okay, I get that.
Right. It dictates how that molten metal droplet actually breaks off the wire. So if you fine-tune the inductance, you can really smooth out that metal transfer. So a smoother detachment.
Exactly. More controlled, more uniform, and the result, way fewer spatters, and the ones you get are finer. Leads to a cleaner, much more consistent weld bead.
That's a great explanation, and that faucet analogy really helps visualize it. So, okay, if inductance offers that kind of surgical control, what if an inspector sees loads of spatter during a visual check?
Right.
What's the immediate red flag beyond just looking messy, and where should their mind go first regarding the settings?
That's an excellent question. Yeah, beyond just being messy, excessive spatter is a big signal. It points to instability in the arc, in the metal transfer.
Okay.
An inspector seeing that should immediately think, okay, are the inductance settings off? Or maybe the voltage or the wire feed speed isn't quite right for what they're doing? It's a clear sign the weld quality itself might be compromised because, uncontrolled spatter often means uncontrolled turbulent metal transfer.
Which could lead to other problems.
Absolutely. Could lead to other defects if it's severe enough. Now, looking at the other options for fine control, option B, using CO2 gas. Well, CO2 is common, sure, but it's actually known for producing more spatter compared to argon-rich mixes. Its arc is just more aggressive.
So the opposite of control.
Pretty much, yeah. It tends to increase it.
Yeah.
Then C, increasing the arc voltage. Generally, that bumps up the heat input, can make the transfer more turbulent, and often increases spatter. The pool gets more agitated.
Right.
And finally, D, welding with no gas. Well, that's just not how MIG-MAG works if you want a quality weld. You need the shielding gas. No gas means catastrophic failure, porosity, oxidation. Far worse problems than just spatter.
So if I'm hearing you right, the inductance isn't just about tidiness, less spatter. It's about achieving this real precision in how the metal detaches, a level of control you just don't get tweaking other things.
That's the heart of it, yes.
Right.
That's the core insight for getting top-tier weld quality.
Fantastic. That gives us great insight into control. The main reason why the use of semi-automatic dip transfer MIG-MAG welding is prohibited for some high-integrity applications is because A, it may produce a lot of spatter. B, the weld metal toughness is always poor. C, it very often gives lack of sidewall fusion defects. D, wire feeding problems mean there are usually far too many stop-start regions. Think about high-integrity applications. Pressure vessels, critical structures, what kind of defect is the absolute deal breaker, maybe even a silent killer in those situations?
Yeah, the correct answer here is C. It very often gives lack of sidewall fusion defects.
Yeah.
This is a huge concern, especially in those high-integrity jobs where failure is just not an option.
Why is dip transfer prone to this specifically?
Dip transfer, or short-circuiting transfer, it operates with relatively low heat input. Now, that can be good for thin stuff or out-of-position welding, but it's a major drawback in thicker sections, or say, complex joints. The way the arc works, short-circuiting, there's a real risk. The weld metal just kind of bridges the gap without properly melting and fusing into the sidewalls of the joint.
Like glue just sitting on the surface.
Exactly like that. It looks joined, maybe, but there's no real bond strength there. It leaves this unfused cold lap, essentially. And that defect is incredibly dangerous because it acts as a stress riser.
Leading to potential failure under load.
Precisely. Catastrophic failure potential. That's why it's often prohibited for critical work.
You categorized spatter earlier, option A, as mostly cosmetic. And structurally, okay, I get that. But couldn't excessive spatter still be a warning sign for an inspector, maybe pointing to other underlying issues that do affect integrity?
Oh, absolutely. That's a really sharp point.
Yeah,
while spatter itself isn't the primary structural defect causing the prohibition.
Yeah.
Excessive spatter is always a symptom. It means the process isn't tuned right, maybe wrong, voltage, wire speed, gas mix. And those underlying issues can indirectly lead to more serious problems.
Like porosity or?
Porosity, maybe lack of penetration if the arc's too unstable. So yes, an inspector should definitely flag excessive spatter as a warning sign, even if lack of fusion is the specific reason dip transfer gets banned for certain jobs. And just quickly on the others. B, weld metal toughness isn't always poor. It can be influenced by parameters and gas, sure, but it's not the main reason for the prohibition.
Okay.
And D-wire feeding problems, well, those are operational headaches. They can happen with any semi-auto process if the gear isn't maintained. It's not an inherent flaw of the dip transfer process itself that leads to a ban.
Okay, let's just absorb that. This isn't just about a tidy weld or things running smoothly. This is safety, reliability, bridges, pressure vessels.
Critical stuff.
Lack of sidewall fusion, a silent killer, often hidden. It just hammers home why understanding the fundamental limits and potential fatal flaws of each process is so vital for an inspector.
Couldn't agree more.
Okay, sticking with materials needing specific handling, let's switch to aluminum. Another one with its own TIG welding hurdles. Question 4. Which of the following current types would be used for welding aluminum with the TIG welding process? A, ACB. DC plus V electrode, dot C. DC plus V electrode, D. All of the above could be used successfully. Now, we know aluminum can be tricky. What are its unique challenges, and how does the current type specifically tackle them?
Right. For TIG welding aluminum, the answer is absolutely, unequivocally A.
Yeah.
AT. This loops back to our chat about surface oxides.
Yeah, like with nickel, but maybe worse.
Exactly. Aluminum's oxide layer is particularly notorious. It forms this aluminum oxide film, which has a much, much higher melting point than the aluminum itself. We're talking over 2,000 degrees C for the oxide versus about 660 degrees C for the aluminum.
Wow, big difference.
Huge. If you try and just melt through that oxide, you end up with a contaminated, weak, basically useless weld. But AC is clever. It gives you that cathodic cleaning action we mentioned during the positive half cycle.
Blasting the oxide away.
Effectively, yes. Electrons flow from the workpiece to the electrode, breaking up that stubborn oxide layer. Then, during the negative half cycle, electrons flow the other way, from electrode to workpiece, providing the heat for penetration, melting the aluminum underneath.
So it's cleaning, then penetrating back and forth.
Continuously. That cycle is absolutely essential for a sound, high-quality TIG weld on aluminum. Without that dual action from AC, forget it. It's almost impossible to get a good weld.
It's amazing how that oxide is almost like a different material sitting on top. Okay, hypothetical. What if a welder just insisted on using DC negative for aluminum? What would the weld actually look like? What feedback does the inspector give?
Well, the inspector would see a mess. Using DC negative on aluminum, the weld would look dull, gray, really dirty, probably riddled with porosity and inclusions.
Arc stability.
Terrible. The arc would likely struggle even to start properly, and it definitely wouldn't clean off that oxide. The bead shape would be awful, poor fusion. You'd have virtually no strength.
So the feedback is pretty blunt then.
Yeah, the feedback has to be clear. This process is fundamentally wrong for aluminum. There's no cleaning action. It simply won't work. And let's quickly touch on why the other DC options are no good. B, DC plus V. Yes, it cleans, but it puts way too much heat onto the electrode. The tungsten would melt rapidly, ball up and contaminate the weld. Highly impractical, damages the electrode.
Okay.
So DC, DCVV. As we just discussed, all heat on the workpiece for penetration, but zero cleaning action. Oxide stays put, leading to massive fusion defects, inclusions. Just bad news.
This really does underline that theme we keep seeing. Understanding the material's basic properties is absolutely critical for picking the right parameters. For aluminum, AC isn't just better, it's the only way, really.
It makes the process possible.
Right. Okay, for our final question today, let's zoom in on a specific, maybe sometimes overlooked component. Question 5. Which of the following welding processes would you expect to use a collet? A, TIG, B, MIG-MAG, C, MA.D, all of the above. Try and picture the inside of each welding torch. Where does a collet fit? What's its specific job?
The correct answer here is a TIG. A collet is a small but absolutely vital piece of kit inside a TIG torch. It's a specialized clamping device.
What does it clamp?
Its main job is to hold the non-consumable tungsten electrode securely in place. The way it's designed allows you to position the electrode precisely and ensures really good electrical contact, which you need for a stable arc.
How does it actually grip it?
When you tighten the back cap on the TIG torch, it pushes down and compresses the collet, causing it to squeeze and firmly grip the tungsten electrode.
It's funny how such a tiny part is so fundamental for TIG. Really shows that as inspectors, you can't overlook anything in the setup, right? No matter how small.
Absolutely.
But what if someone, maybe someone new, accidentally tried to jam a TIG collet into a MIG torch? Or the other way around? I mean, obviously it wouldn't work, but what's the basic design clash? Why is it impossible?
Yeah, that's a good practical thought. The fundamental clash is simple. They're designed for completely different ways of delivering the electrode. For MIG-MAG, option B, the electrode is a wire that's continuously fed. It's consumable. A collet just wouldn't work with that feeding mechanism.
Right, MIG has a contact tip instead.
Exactly. A contact tip guides the wire and transfers the current as it shoots through. Then for MMA, option C, or stick welding, the electrode is a coated stick that you grip externally.
With the electrode holder, the stinger?
Right. There's no need for an internal gripper like a collet because you use up the stick and replace it, holding it externally. So trying to swap those parts, square peg, round hole, totally incompatible with how each process fundamentally works.
That makes total sense. It's all about how the electrode gets to the arc. These kinds of details, even about small parts like collets, really matter for an inspector, don't they? Because they tell you about the mechanics and the quality control for each method.
Knowing the components helps you spot problems and ensure things are set up right. Definitely.
Okay, and that brings us to the end of this deep dive. We've covered some really crucial territory today, building out that inspector's roadmap. We tackled the precision you get with inductance control in MIG-MAG, explored those material-specific choices for TIG nickel alloys, aluminum, the AC/DC differences.
Yeah, the oxides.
Exactly. And highlighted those critical safety issues with processes like dip transfer and high-integrity work, that lack of fusion risk.
Very important.
We even drilled down into essential bits like collets. Dissecting these exam-style questions, it's not just about passing the test. It really shores up your practical understanding for whatever you face out there.
Precisely. And as we've seen today, every single choice parameter, component, current type has a ripple effect. It impacts the final weld integrity, whether it's suitable for the job.
Right.
Which I think raises an important question for you, the listener, to mull over. Beyond just knowing the right answer for an exam, how does truly understanding these underlying principles, the why behind the what, how does that empower you to critically assess quality, to ensure safety in any welding situation you encounter?
That's a great point.
Think about how these individual bits of knowledge connect, how they build up into a more complete, holistic understanding of welding quality. That allows you to be a much more proactive and effective inspector.
A fantastic thought to leave everyone with. Thank you for joining us on the deep dive. We really hope this session has been valuable for your CSWIP 3.1 exam prep and just for your journey to becoming an even more knowledgeable welding inspector. We'll catch you next time.